This is a solar-powered engine that uses no electricity and burns no fuel. Instead, it runs using nothing more than the sunlight and the physics of thermal radiation. One side of the engine is coated with the blackest paint in the world that absorbs nearly all incoming visible light, while the other side is coated with a special radiative cooling paint that can stay cooler than its surroundings by emitting heat to the sky. In this video, I'm going to be talking about something called a black body and how these black bodies emit radiation, and then compare it to how regular objects emit radiation, and then show you how you can use these properties to your advantage to stay cool and produce meaningful work as well. Now, before we continue, I want to thank Delete Me for sponsoring this video. Privacy is something that's important to everyone. Unfortunately, there are hundreds of data broker websites that collect and sell personal information. In many cases, that information can be accessed by almost anyone. That's why I've been using Delete Me for over 2 years now. Delete Me is a subscription service that finds and removes your personal information from hundreds of data broker and people search websites. And they continue monitoring those sites over time to help keep your information from reappearing. They regularly search hundreds of websites for your personal information and handle the removal process in your behalf, saving you from having to track down and contact these sites yourself. Look how many websites they've reviewed and then removed my personal information from, all without me lifting a finger to do anything. One thing I really like about Delete Me is that they don't just blindly submit removal requests. They first verify that your information is actually present on a site before taking action. They also have privacy advisors available if you need help. And if you find your information somewhere online that you'd like to be removed, you can submit a custom removal request and Delete Me will take care of it. Delete Me has been helping people remove personal information from data broker sites for more than 15 years and was recently named Wirecutter's top pick for data removal services. So if you'd like to see what personal information may be floating around online about you and help get it removed, go to joindeleteme.com/actionlab and use code ACTIONLAB for 20% off Delete Me consumer plans. And thanks again to Delete Me for sponsoring this video. Now let's get back to our experiment. In my last video, I showed you a radiative cooling paint called cryopaint. This is a special type of paint that emits radiation right near the atmospheric window, where the sky is very cold, so that it thermally connects with the cold sky to radiate heat very efficiently. So if it begins to heat up, it sends out more radiation than it receives and it cools down and stays cool even in the hot sun, and in some cases colder than the shade. I even used it to make some clothes that keep you cool in the sun. But I didn't go very deep into how this paint works. So in order to understand this, you have to know that atoms and molecules have the ability to absorb or emit electromagnetic waves in 3 different ways. The highest energy way they can emit or absorb light is through electrons jumping to different orbitals. This happens with UV light down to visible light. In atoms, electrons can only exist in certain allowed energy levels. They can move between these energy levels when they absorb exactly the right amount of energy, either from a photon of light or from a collision with another atom. When an atom absorbs a photon whose energy matches the difference between these 2 energy levels, the electron moves to a higher energy state, storing that energy within the atom. Later, the electron can fall back to a lower energy state and release the energy as a photon of light. This means that any atom that can emit a particular wavelength of light when it gets heated up can also absorb that same wavelength very efficiently, because both processes involve the exact same energy transition between these quantum states. But what about non-visible light like infrared light? Well, at these lower energies, the electromagnetic waves don't make electrons jump orbitals, but instead it changes how the atoms and the molecules vibrate. So for example, if you have some atoms bonded together and shine some infrared light on them, depending on the wavelength of the IR light, it will cause the molecules to vibrate with a certain resonant frequency. Or if you just excite the molecules with heat, they will radiate infrared light. So a specific resonant frequency of the atoms vibrating will absorb or emit a specific frequency of infrared light. And when the electromagnetic waves get even lower energy, such as microwaves or radio waves, molecules can absorb and emit those wavelengths through rotational motions. For example, in your microwave, the oscillating electric field causes the polar molecules like water to rotate back and forth, converting that energy into heat. So if you look at some molecule or object and the whole electromagnetic spectrum, you can graph out its absorption or emission spectrum for all the wavelengths of light that will affect its electrons, vibrations, and rotations. and you end up with a graph like this. But physicists said, what if there was some material that absorbed every single wavelength across the entire spectrum 100%? They called this theoretical object a black body. Black bodies are the easiest type of radiation to deal with because they absorb all wavelengths perfectly. So their absorption-emission spectrum is just a straight line. But that doesn't mean it can just magically produce any wavelength of light. It has the potential to emit the light, it just needs the energy to do so. So this means as you heat a black body up, it will start to release a range of wavelengths of light. The higher the temperature, the more that emitted spectrum grows until it covers the whole spectrum. So this curve is very important in physics. It's called the black body emission spectrum. Now when we turn up the temperature, notice that the energy emitted increases like crazy. So it's hard to see the shape of this graph without zooming out like a lot. So in this video, I'm going to normalize the black body emission spectrum so that it's always divided by its maximum. So now on the curve, the max will always be 1 when I turn up the temperature. Then we can see how the shape changes as we move the temperature. Now this is where we can finally start to understand the cryopaint or other radiative cooling paints. They're made from ceramic particles that naturally vibrate right around the 10 micron wavelength. This specific wavelength is important, as I showed in the last video, because it's right in the range where the sky radiates the least energy. So it can use the sky as a heat sink. This spectrum is interesting because notice how it drops off on both sides. This means that it only absorbs radiation and emits it right in this small window. But again, this is only its potential to emit radiation. Its real emission depends on its temperature. So if I multiply its spectrum by the black body emission curve, then I get this curve that shows the emission lines at a given temperature for the cryopaint. You can see the emission change at different temperatures. Now when I overlay the black body emission on top of it, you can see that I always stay below the black body emission. It's boxed in by its emission spectrum shown here in red. But if that's true, notice something interesting. A perfect black body actually emits even more thermal radiation than cryopaint. So shouldn't a black body cool even better? Well, I have something here that's very close to a black body. This is called IR flock sheet. It absorbs over 99.7% of visible light and also absorbs over 99.5% of infrared across the spectrum. So this is the IR flock sheet, and this is the Kawami black, which absorbs almost all visible light but not infrared light. When I shine an infrared light on it and film with an infrared camera, you can see how black the IR flock sheet is compared to the sheet that only absorbs the visible light. So if there were no other incoming source of radiation, like at night with no sun, then this black body-like surface would actually radiate heat away faster than the cryopaint and could cool down even more quickly. So what makes cryopaint or radiative paint so special then? Well, the answer is that there's sunlight out there during the daytime. Notice that cryopaint emits strongly in the atmospheric window, but it doesn't absorb most of the incoming visible light. The black body-like surface, on the other hand, absorbs nearly all of that sunlight and converts it into heat. So even though the black body is a better emitter than the cryopaint, it'll still heat up more because it absorbs so well in the visible light range as well. So now that we understand this better, let's see if we can actually use this property of cryopaint to our advantage. I have something called a Stirling engine here. This engine operates by expanding air when the air is on the hot side and then contracting when the air is on the cold side. So if you can supply a side that's continually hot and a side that's continually cooler, then you can make the engine run. So for my hot side, I'm going to use a paint called Musso Black. It has an absorptivity of around 99% in the visible range. Then I'll paint the top of the Stirling engine with the cryopaint, which will act as the cool side. I'm also going to put this thermal paste on it to connect the hot side to the metal heatsink of the Stirling engine. Now let's take it outside and see if it starts running on its own. Okay, let's see if this actually works. Okay, this actually works. I did not think it would work. So the top staying cool enough to be the cold sink and the bottom staying hot enough to be the hot sink. Look at that. That is so cool. I can't believe it works. Now we know that we can make an electric engine by using solar panels, but this is cool because it works without electricity. So So the way this is working is because the black's able to very efficiently absorb the light and convert it to heat. But the cryo paint doesn't absorb heat and still radiates well into the sky, so it stays much cooler. And thanks for watching another episode of the Action Lab. I hope you learned something. If you haven't subscribed to my channel yet, remember to hit the subscribe button, and we'll see you next time.